You know, the buzz around artificial intelligence and deep learning right now, it's just incredible, isn't it?
No, absolutely. It
Yeah.
really feels like we're on the cusp of something huge.
Definitely transformative.
Hmm.
But for a lot of people, myself included, sometimes really understanding what's actually going on under the hood.
Yeah, what these things are, how they work.
Exactly. It can feel, well, a bit daunting, overwhelming even. So, welcome to the deep dive. This is where we take a whole stack of information, often complex stuff, and we distill it down. We find those absolute must-know nuggets.
Helping you get genuinely well-informed, but without feeling completely swamped by it all.
Precisely. This deep dive is designed just for you, and it's brought to you by our friends at easymasterai.com. Today, we are diving into a fantastic resource. It's called A Visual Introduction to Deep Learning by Meor Amer.
Sounds interesting already. Visual introduction.
Exactly. And our mission here is really to cut through all that information overload that the author himself highlights. We want to help you build a real visual intuition.
Get that gut feeling for how deep learning and neural networks actually operate.
Yeah, make these complex ideas feel, well, clear.
And what's great about this book, from what you're saying, is how approachable it is. The author makes it clear, right? It's for you if you're totally new.
Right, completely new to deep learning or machine learning.
Or even if you've got some background, but you're looking for that deeper kind of visual grasp of things. It seems like he's really aiming to compress a lot of complex knowledge into something, digestible.
And when you hear the author's personal story, it really clicks why the book works so well. His whole journey into AI started back in 2010.
Oh, wow.
Yeah, after his son was born with a limb difference. That actually led him to explore machine learning specifically for prosthetics.
That's powerful motivation.
It really is. And he also has this solid background in telecoms data analytics.
Yeah.
So he's got the tech chops too.
And you can feel that passion, right? For education, for finding alternative ways to learn.
Yeah,
using visuals, stories, even games.
yeah.
It sounds like that really shines through in the book's format.
Totally. It's very much a visuals first kind of approach. The text is concise, clear.
And crucially, minimal math derivations or code examples you mentioned.
Exactly. Which just makes it incredibly accessible for, almost anyone who's curious.
Okay, so for our deep dive today, how are we going to tackle this? What's the roadmap?
Right. So we'll basically navigate through the core concepts just like the book does. We'll kick things off with the big picture, why deep learning is such a big deal right now, what's driving all this progress.
Okay, the context first.
Then we'll ground ourselves in the fundamental building blocks, the neuron itself, and the absolutely critical role of data.
Makes sense. Foundations first.
Then we get practical. We'll walk through the book's examples, exploring how these neural networks actually learn to tackle 4 different kinds of tasks.
The regression and classification examples.
Yep. Linear regression, then nonlinear regression, then binary classification like yes, no, and finally multi-class classification.
So building up complexity step by step.
Exactly. And then finally, we'll kind of zoom back out. We'll look at some other important neural network architectures you hear about and some key things to think about for actually making these models perform well.
Okay, sounds like a solid plan. A real journey from the basics up to the bigger picture. Let's unpack this.
Okay, so the book kicks off by connecting something really fundamental prediction to how we make decisions.
Right, making decisions when things are uncertain, which is basically all the time.
We do it constantly, and the more experience we have in life, generally, the better our predictions get.
Think about translating languages or driving a car, or even in business, like figuring out which customers might leave. Those are all predictions, really.
And here's where it gets really interesting, right? Machine learning can actually automate these predictions.
Exactly. But instead of life experience, the machine's experience is just data. Tons and tons of data.
It learns patterns from that data just like we learn from experiences.
And the book brings in prediction machines, which argues that machine learning offers predictions that are often better, faster, and crucially cheaper than what humans can do alone.
Better, faster, cheaper. That's quite a claim.
It is. And that capability allows us to scale up our efforts massively. We can tackle more challenges, speed up progress in so many areas.
But then there's that question that always comes up. Is this the end of human jobs?
The author tackles that directly. He mentions that World Economic Forum report from 2020,
Yes.
which estimated, even with pandemic effects, something like 97 million new roles emerging by 2025, compared to maybe 85 million displaced.
So a net positive, actually.
Yeah, it points towards job evolution,
Yeah.
not just elimination. The idea is machines handle the prediction side, freeing us humans up for more creative, strategic, uniquely human work.
That makes sense. Okay, so when should we actually turn to machine learning?
The book lays out this neat little progression. First, there's just human judgment. Then, maybe we try to write down specific rules, like in software rules-based systems.
If this, then that.
Exactly. But then, when the data gets really complex, or the rules become too numerous or subtle to write down,
That's when ML comes in.
that's where it shines. The machine learning system can create its own rules from the data, guided by the goals we give it. It finds patterns we might never spot.
In deep learning specifically, what makes it special within machine learning?
Well, deep learning is a particular type of machine learning algorithm. It's not always the absolute most accurate for every single problem, but its real strength is its flexibility.
Adaptability.
Yeah, it's modular. You can build these complex structures, which makes it incredibly good at handling a huge range of data types and complexities. Super versatile.
So why the big explosion now, if the ideas have been around?
Right. The book points to this convergence, this perfect storm of three things hitting at once.
Okay, what are they?
First, the algorithms. Like you said, many core ideas aren't brand new. They've been developing for decades.
Okay.
Second, data. Just the sheer volume and variety of data we have now, thanks to the internet, social media, smartphones, it's unprecedented, the raw fuel for learning.
Got it. Data is everywhere.
And third, computation.
Yeah.
This is a massive one. GPUs, graphics processing units.
Originally for video games, right?
Exactly. But they turn out to be perfect for the kind of parallel calculations deep learning needs. Way faster than traditional CPUs for this stuff.
Yeah.
And that hardware is still getting better and better.
Wow. Algorithms, data, computation, the trifecta.
Pretty much.
Yeah.
And when those three click together, suddenly we could build applications that actually work in the real world.
Like computer vision, classifying images, detecting objects.
Natural language processing, translation, understanding sentiment.
And loads of business automation. It feels like it's just getting started.
Absolutely. So coming back to the book, what's the promise? What will you walk away with?
The core promise is that visual intuition, understanding how deep learning and neural networks work conceptually.
Without getting lost in complex math proofs or lines of code, at least initially.
Right. Those are important next steps if you want to go deeper, but this book focuses on building that solid foundation first.
Makes sense.
Yeah.
And it does that through those four tasks.
Exactly. It structures the learning really logically. Linear regression first, simplest case, then nonlinear regression, then binary classification, then multi-class. Each chapter builds on the last.
Starts with foundations, ends with the bigger picture. Seems like a really well thought out journey, plus summaries to revisit key ideas. That's helpful.
Definitely. It's comprehensive but stays accessible.
Okay, so let's dive into those foundations. First off, the terms deep learning and neural network.
Yeah, the book points out they're often used interchangeably.
Which is true, but maybe neural network feels a bit more concrete when you're talking about the actual nuts and bolts, the structure itself.
Agreed. So if we're talking neural networks, we have to start with the absolute smallest piece, right?
A fundamental unit,
Mm-hmm.
and that's the neuron.
So what is a neuron in this context? It's not biological, obviously.
Right. Think of it as a tiny computational unit. It takes in some numbers as inputs,
Okay, just numbers.
performs a couple of mathematical operations,
Yeah.
and then spits out an output number.
Simple enough. What are the operations?
First is the weighted sum. Each input number gets multiplied by its own specific weight.
Like how important is this input?
Exactly. It's like a dial controlling the influence of that input. Then all those weighted inputs are just added up, and usually a bias term is added too.
Bias.
Yeah, think of it as an extra adjustable number, kind of like a starting point or an offset for the neuron. That gets added in regardless of the inputs.
Okay, so weights, multiply inputs, sum them up, add a bias. And these
Yeah.
weights and biases,
Oh,
they're important, right?
hugely important. They are the parameters of the network. These are the knobs and dials that the network actually learns to adjust during training. That's how it adapts.
Got it. So that's the first calculation. What's the second?
The result of that weighted sum plus bias then gets passed through an activation function.
Activation function. Sounds technical.
It is, but it's crucial.
Yeah.
This is what gives the network its power, its ability to learn complex patterns, not just straight lines. It introduces nonlinearity.
Nonlinearity. Okay, we'll probably come back to why that's so important.
Definitely. For now, just know it's the second key step inside the neuron.
All right, so that's the neuron. But you mentioned earlier, they need fuel.
Absolutely. The book puts it bluntly. Neural networks are nothing without data.
Data is like experience for humans.
That's a great analogy. The network sifts through data, finds patterns, finds relationships, and uses those insights to learn, basically to update those weights and biases.
Makes sense. And data isn't all the same, right?
Not at all. You've got structured data, nice, neat tables like spreadsheets, hotel rates, customer records.
Easy to work with, relatively.
Yeah. But then there's unstructured data. Text, images, audio, video, just raw stuff.
And that's most data.
Increasingly, yes. The book mentions a projection that by 2025, something like 80% of all data worldwide will be unstructured. And that's where deep learning has made huge strides.
Wow. Okay, so how do we organize this data for network?
A collection of data is called a data set. And each individual piece of information, like one specific hotel's details, is a data point.
And that data point has characteristics.
Right, those are called features. So for our hotel, features might be distance from city center or guest rating.
And what are we trying to predict about that hotel?
That's the target, or sometimes called the label. It could be the hotel's price, or maybe whether it's likely to be fully booked.
So we give the network the features and the target answer during learning.
Exactly. When we provide both the inputs, features, and the desired outputs, targets, that's called supervised learning. And that's the main focus of this book. We're supervising the learning process.
Okay, so you feed it the supervised data. What happens then?
That's the training phase. The network processes the data, makes predictions, compares them to the actual targets, calculates the error.
And uses that error to adjust its weights and biases.
Precisely. Over and over again. The end result is a trained model.
Yeah.
You might hear people say they're fitting the model to the data.
Fitting the model, okay. But how do we know if it actually learned well, not just memorized the training data?
Excellent question. That's why we need testing. You hold back a chunk of your data that the model never sees during training.
The test set.
Right. Once the model's trained, you feed it this unseen test data and see how well it predicts the targets. That gives you a much better idea of how it will perform on new, real-world data.
All right, let's get concrete. How do these networks actually do things? Let's start simple. Task 1, linear regression.
Okay, so the goal here is basic. Predict hotel price, but only based on one feature, distance from the city center.
And in this specific example, the book sets it up so that relationship is just a straight line.
Exactly. Price goes down steadily as distance increases, a simple linear relationship. And because price is a continuous number, it's a regression task.
So how does the network learn this straight line?
This is where that four-step training cycle the book emphasizes really comes into play. It's predict, measure, feedback, adjust.
Predict, measure, feedback, adjust. Okay.
And this cycle just repeats over and over for many rounds, called epochs.
So step 1, predict.
The training data, distance, goes into our single neuron. It calculates the weighted sum, adds the bias.
It uses its current weight and bias setting.
Right, and then passes it through the activation function. For this linear task, we use the simple linear activation function output equals input. It predicts a price.
Okay, it makes a prediction. Then step 2, measure.
How good was that prediction? We compare it to the actual price from the training data and calculate the error, the difference.
And we need a way to summarize all those errors.
Exactly. That's the loss function. Here, it's mean squared error, or MSE. Square the errors so positives and negatives don't cancel out and big errors hurt more than average them. The network's goal is to make this MSE as low as possible.
Minimize the mean squared error. Got it. Now, step 3, feedback. This sounds like the important part.
It is. This is where the learning happens. The neuron needs to know how to change its weight and bias to reduce that MSE next time.
How does it figure that out?
The book uses a great visual. Imagine plotting the MSE for every possible value of the weight. You get this U-shaped curve, the loss curve.
And the bottom of the U is the best weight value, the lowest error.
Precisely. The goal is to get to the bottom of that curve. The gradient tells us the slope or steepness of the curve at our current weight's position.
Steep slope means we're far from the bottom.
Generally, yes. The gradient tells us two things. Its magnitude, how big the slope is, tells us roughly how much to adjust, and its sign, positive or negative, tells us which direction to adjust the weight to go downhill on the curve.
Ah, so it's like rolling a ball down the hill to find the bottom.
That's the essence of gradient descent. The book shows how to calculate these gradients for the weight and the bias based on the input and the error. It's the feedback signal.
Okay, so it gets the feedback. Then the final step, adjust.
Right. The neuron uses those calculated gradients to update its weight and bias. But it doesn't just jump straight there. It uses a learning rate.
The alpha value.
Yep, usually a small number. It scales down the gradient adjustment. This ensures the neuron takes small, careful steps down the loss curve.
Not overshoot the bottom.
Exactly.
No.
Too small a learning rate, it takes forever. Too large, it might bounce around wildly and never find the minimum. Finding a good learning rate is key.
Okay, predict, measure, feedback, adjust. Repeat many times makes sense. The book mentioned cost and metric.
Right. Cost is usually the average loss, like MSE, over the training data. That's what the algorithm tries to minimize internally. Metric is what we look at to judge performance, often the same thing for a regression, MSE, but maybe something more interpretable.
So after, say, 100 epochs of this cycle,
the model settles on a weight and bias that define a pretty good straight line through the data points. The training MSE might be low, like 16.4 in the book's example.
And then you check it on the test data it hasn't seen.
Yep. The test MSE will likely be a bit higher, maybe 144.5 here because it's unseen data, but hopefully still in a reasonable range, showing it generalized.
Now, you could use simpler math for a straight line. Why use a neural network here?
It's purely foundational. This simple case lets us understand the core mechanics, the neuron, weights, bias, activation, loss, gradient descent before we add complexity. The real power comes next. Okay, task 2, nonlinear regression. What happens when the relationship isn't a nice straight line?
Right, because a single neuron or even a network using only linear activation just can't model curves or complex patterns.
Mathematically, stacking linear layers is still just linear. You need something more.
So we need a proper neural network with layers.
Exactly. Now we introduce hidden layers between the input and output. Data flows input, hidden output. Each neuron in each layer does its weighted sum and activation.
And these hidden layers, what do they do?
They act like feature extractors or transformers. They take the initial inputs and combine them, transform them, looking for more complex patterns and signals that help the final output layer make better predictions.
Okay, so for this task, we're still predicting price, but now using two features, distance and guessed rating.
Right. And with more data points, the book shows the distance-price relationship isn't linear anymore. It looks more like a curve, maybe bowl-shaped, definitely nonlinear.
So the network structure needs to change.
Yep. Input layer now has 2 neurons, one for each feature. The book uses one hidden layer with, say, 3 neurons, and still one output neuron for the price prediction.
How do you choose 3 hidden neurons?
That's part of the art. It depends on data complexity. More layers of neurons allow for more complex functions, but risk overfitting. You often experiment.
Okay, so we train this network using the same 4 steps: predict, measure, feedback, adjust. What happens if we still use only linear activation in that hidden layer?
Disaster. The results are terrible. High MSE, predictions look random. It confirms. Linear activation, even with hidden layers, still produces only linear relationships, like a flat plane in 3D space in this case.
So this is where that nonlinearity we skipped over becomes critical.
Absolutely.
Yeah.
We need to introduce a nonlinear activation function in the hidden layers. The book introduces a really popular and effective one, ReLU.
ReLU, rectified linear unit, what does it do?
It's incredibly simple. If the input to the neuron after the weighted sum plus bias is positive, ReLU just passes that value through unchanged.
Okay.
But if the input is negative, ReLU outputs 0.
0, so it just shuts off if the input is negative.
Kind of. It acts like a gate. It gives the neuron a choice, either pass the signal or block it. This simple on-off, nonlinear behavior is what allows the network to start approximating complex curves and shapes.
That little change makes such a big difference.
Huge difference. You replace the linear activation in the hidden layer with ReLU, run the training again.
And the performance dramatically improves.
Exactly. Much lower MSE. The prediction curve now actually captures that nonlinear bowl-shaped relationship in the data.
Wow. And adding more layers or neurons could make it even more detailed.
Potentially, yes.
Yeah.
More capacity to model finer details, though you have to be careful not to just memorize the training data.
Okay, so ReLU is key for nonlinearity. Are there others?
Yes, several others, but ReLU is a very common and effective starting point for hidden layers. We'll see different ones for the output layer next. All right, moving on. Task 3, binary classification.
So we're shifting gears now, right? Not predicting a number like price, but predicting a category.
Exactly. Regression was about continuous values. Classification is about assigning things to predefined groups or classes.
Like, is this email spam or not spam? Is this picture a cat or a dog?
Perfect examples. Or, in the book's case, using the same hotel features, distance rating, predict if the hotel is hot meaning high demand, yes or no.
Yes, no. Two categories. That's binary classification.
Correct. And the book highlights two main changes needed compared to regression:
What are they?
the activation function in the output layer and the loss function used for training.
Okay, so the input layer, two features, and hidden layer, say 3 neurons with ReLU, can stay the same.
For this example, yes, the hidden layers are still finding useful patterns, but the final output needs to represent a yes-no probability.
How do we get a probability? Prices can be anything, but probabilities have to be between 0 and 1.
That's where the sigmoid activation function comes in for the output neuron.
Sigmoid, what does that do?
Its magic is that it takes any incoming number, no matter how large or small, and squishes it neatly into a value between 0 and 1.
Ah, perfect for probabilities.
Exactly. So the neuron's output can be directly interpreted as the probability of the hotel being hot. If it outputs 0.8, that's an 80% chance.
And then you just set a threshold, like above 0.5 means yes, 1, below 0.5 means no.
Precisely. You discretize the probability output to get the final class prediction.
Okay, so that's the output activation. What about the loss function? Can we still use mean squared error?
You could, but it doesn't work very well for classification. MSE can create a loss landscape with lots of local minimums, little dips, where the network can get stuck thinking it's found the best solution when it hasn't. It's non-convex.
Not ideal. So what's the alternative?
For binary classification, the standard is binary cross-entropy.
Binary cross-entropy. Okay, why is it better?
It's mathematically designed to be convex for this type of problem, meaning it has one clear minimum point, making it much easier for gradient descent to find the optimal solution. It strongly penalizes the network when it's confidently wrong about the class.
So it effectively pushes the sigmoid output towards 1 when the true answer is 1, and towards 0 when the true answer is 0.
That's the idea. It guides the learning process much more effectively for classification tasks.
Got it. So training still uses the 4 steps. Predict with sigmoid output, measure with binary cross-entropy loss, feedback, calculate gradients, adjust, update weights biases.
Yep, the core cycle remains the same.
But how do we measure performance now? MSE doesn't feel right for yes-no answers.
Good point. The common metric for classification is accuracy. What percentage of predictions did the model get right?
Simple enough. But you mentioned earlier accuracy can be misleading.
It absolutely can be, especially with imbalanced data. Remember the fraud example. If only 1% of transactions are fraud, a model predicting no fraud 100% of the time gets 99% accuracy.
But it's useless because it misses all the fraud. Okay, so accuracy isn't the whole story.
Definitely not. We need a more detailed picture. The book introduces the confusion matrix.
Confusion matrix. Sounds confusing.
Huh. It's actually very clear once you see it. It's just a table showing how many predictions were. True negatives, correctly predicted no. False positives, incorrectly predicted yes. False negatives, incorrectly predicted no. And true positives, correctly predicted yes.
Ah, okay. So it breaks down how the model was right or wrong.
Exactly.
Yeah.
And from that matrix, we can calculate better metrics like precision and recall.
Precision and recall. What do they tell us?
Precision asks, of all the times the model predicted yes, how often was it actually correct? Recall asks, of all the actual yes cases, how many did the model correctly identify?
I see. They focus on the positive class predictions and avoid being skewed by too many true negatives.
Right. And often people use the F1 score, which is a balanced average of precision and recall. Gives you a single number reflecting both aspects.
Okay, that seems much more robust than just accuracy. So for the hotel data,
the model gets good accuracy, maybe 92%, and the precision and recall scores are also strong and fairly balanced, suggesting the dataset isn't heavily skewed. And again, a bigger network can push accuracy even higher, creating clearer separation between the hot and not hot hotels.
Okay, binary was 2 classes. What if there are more? Like the hotel certification, gold, silver, or bronze?
Now we're in multi-class classification. Same principles, just scaled up a bit.
How do we handle the output? We can't just use 0 and 1 anymore.
Correct. The book introduces one hot encoding for the target data. Instead of one column with gold, silver, or bronze, you create 3 new columns, one for each class.
Okay.
So a gold hotel gets a 1 in the gold column and Zorro's in the silver and bronze columns. A silver hotel gets a 1 in the silver column, zeros elsewhere, and so on.
Ah, so each class gets its own binary target column. Clever.
It works well. Now, for the network architecture, input and hidden layers with ReLU can be similar, but the output layer needs to change again.
Oh.
Yes. You now need one output neuron for each class. So 3 output neurons in this case. One for gold, one for silver, one for bronze.
And the activation function for these 3 neurons can't be sigmoid. That's for one output between the 0 and 1.
Right. Here we use the softmax activation function.
Softmax, what's its trick?
It does 2 things across all the output neurons together. First, it uses exponentiation to make all their outputs positive and emphasize the larger ones. Second, it normalizes them, divides each neuron's output by the sum of all their outputs.
What does that achieve?
The magic is that the resulting outputs for all the classes now sum up to exactly 1.
Oh, so you can treat them as probabilities again. Probability of gold, probability of silver, probability of bronze, all adding up to 100%.
Precisely. Then the network's final prediction is simply the class corresponding to the neuron with the highest probability output.
Very neat. And the loss function. Binary cross-entropy was for 2 classes.
We need its multi-class cousin, categorical cross-entropy. It's the same core idea. Push the probability of the correct class's neuron towards 1 and the others towards 0. Works for any number of classes.
Okay, so similar training cycle, just with softmax output and categorical cross-entropy loss. How does it perform?
The book shows it achieves good accuracy, like 96% on training data. A larger network helps define the decision boundaries between gold, silver, and bronze even more clearly. Test accuracy might be lower, say 75%, but still shows generalization.
And the confusion matrix just gets bigger, like a 3x3 grid.
Exactly. And you can calculate precision and recall for each class individually. Gold precision, gold recall, silver precision, silver recall, etc., to see where the model excels or struggles.
Okay, we've seen how networks learn these different tasks, but building a really good model involves more tuning, right? The book talks about parameters versus hyperparameters.
That's a crucial distinction. Parameters are the weights and biases, the things the network learns automatically through gradient descent.
The internal dials.
Right. Hyperparameters are the settings we, the humans, choose before training starts. Things like the learning rate, the network structure.
They're like external dials we set to guide the learning process.
Exactly. And choosing good hyperparameters is critical for performance. It's often an experimental process, part art, part science.
What are some key hyperparameters the book mentions?
Well, the size of the network is a big one. How many hidden layers and how many neurons, units, in each layer. Bigger networks can model more complexity, but are slower and risk overfitting.
Finding that Goldilocks zone.
Pretty much. Then there's the activation function choice. We saw ReLU for hidden layers is common, but the output layer's activation, linear, sigmoid, softmax, totally depends on the task.
Right. Regression, binary classification, multiclass.
The learning rate, alpha, is super important. We talk about that. Too high is unstable, too low is too slow.
Getting that gradient descent just right.
Yep. Also, the number of epochs, how many times you cycle through the training data. Too many can lead to overfitting.
Where it just memorizes the training noise.
Exactly. Too few leads to underfitting, where it hasn't learned enough. Techniques like early stopping, monitor performance on a validation set, and stop training when things stop improving.
Smart. Avoids unnecessary training.
And for large data sets, you don't usually process everything at once. You use batch size.
Splitting the data into mini batches.
Right. The size of those batches is another hyperparameter we choose.
And mini batching isn't just about memory limits, is it? The book mentioned a balance.
Correct. Updating weights after every single data point to cast a gradient descent can be noisy. Updating only after the entire data set, batch gradient descent, is slow. Mini batching hits a sweet spot, faster updates than full batch, but more stable than fully stochastic. It's usually the preferred method.
Okay, those are hyperparameters. What about techniques related to the data itself?
Good question. The book mentions k-fold cross-validation.
That sounds complex.
The idea is simple, really. Instead of one train to split, you split the data into, say, 5 folds, k5. You train on 4 folds and test on the 5th, then train on a different 4 folds, test on the held-out one. Repeat 5 times, so each fold gets used as the test set once.
Why do that?
It gives a much more robust estimate of the model's performance, especially if your dataset is small. It helps ensure your results aren't just due to one lucky or unlucky split, and helps combat overfitting.
Makes sense. Get a more reliable average performance.
And in practice, people often use 3 splits: training, validation, and test.
What's the validation set for?
You use the training set to learn the weights biases. You use the validation set during development to tune those hyperparameters like learning rate, network size, and decide when to use early stopping.
Ah, so it's like an intermediate test set for tuning.
Exactly. Then, the final test set is kept completely separate, locked away until the very end. You only use it once after all tuning is done to get the final unbiased measure of how well your model will likely perform on brand new, unseen data.
That seems like a really rigorous way to evaluate performance.
It's best practice. Okay, so we've covered the basics in tuning. The book then zooms out further, right, to other types of networks.
Yeah, because the examples we walked through were all feed-forward neural networks. Information just flows straight from input to output.
But there are other architectures designed for specific data types, like convolutional neural networks, or CNNs.
Those are big in image processing, aren't they?
Absolutely. Instead of connecting every input pixel to every neuron in the first layer, CNNs use small filters or kernels that slide across the image.
Like little magnifying glasses looking for specific patterns. Edges, corners, textures.
That's a great way to think about it. They learn hierarchies of features, leveraging the fact that nearby pixels are related. Super powerful for image classification, object detection, finding where things are in an image, even segmentation, classifying every single pixel.
Cool. What else?
Recurrent neural networks, or RNNs. These are built for sequences data where order matters.
Like text. Or stock prices over time. Music.
Exactly. The key idea in RNNs is that they have a memory element. The output from processing one step in the sequence is fed back in as an input to the next step.
So it remembers what came before.
In a sense, yes. This allows them to understand context and language, predict the next word in a sentence, translate languages, even generate text or music.
Fascinating. And then their GANs, those sound futuristic.
Generative adversarial networks. These are really interesting. What if you want the network to create new data, not just classify or predict?
Like generate realistic images.
Precisely. A GAN actually has two networks that compete. A generator tries to create fake data, like images, that looks real. A discriminator tries to tell the difference between the real data and the fake data from the generator.
So they're adversaries, learning from each other.
Exactly. The generator gets better at fooling the discriminator, and the discriminator gets better at spotting fakes. They push each other to improve, resulting in incredibly realistic generated data.
Wow. That's a whole different level.
And the book mentions these are just examples. There are other important architectures like transformers, the basis for models like ChatGPT and graph neural networks for relational data. The field is constantly evolving.
It really is an exciting time.
So wrapping up the book's view.
It concludes that deep learning has enormous potential. It can help tackle major global challenges. It's not a magic bullet for everything, but its versatility is making a massive impact across so many industries.
And it emphasizes that it's still a relatively new field. Lots of room for innovation, lots of opportunities still wide open.
Yeah. And it ends by circling back to the key concepts, reinforcing that visual intuition, and suggesting resources for anyone who wants to dive deeper into the math or the code next.
Wow. Okay. That was quite the journey through a visual introduction to deep learning. We really went from the single neuron
all the way through different tasks, training, hyperparameters,
and even touched on complex architectures like CNNs, RNNs, and GANs.
Hopefully listening to this has helped build some of that visual intuition the author aimed for, those aha moments. Yeah, truly getting a feel for what's actually powering this AI revolution around us.
So here's a thought to leave you with. Now that you have a clearer picture of these foundational pieces, these building blocks, what might you explore next? Or maybe even, what could you build with this knowledge? How might you play a part in this incredibly exciting future of AI?
That's a great question to ponder. This deep dive was brought to you by EasyMasterAI.com.
That's EasyMasterAI.com.
Definitely check out their website, EasyMasterAI.com, to learn even more about artificial intelligence and also discover some really powerful tools that can actually help you make money with AI.
Lots of great resources over there.
Absolutely. Visit EasyMasterAI.com.